I've got two glasses of water here, and one of them's got salt dissolved into it, so which one is which? And that brings up the question of the day, which is, which boils hotter, salt water or regular water? Now, to explain this, we have to go back and talk about two things, the water molecules and the salt molecules. And so let's first talk about what's going on with salt. Before salt combines chemically, sodium atoms have 1 valence electron and chlorine atoms have 7 valence electrons. And we know that because we count the number of columns in the periodic table. Remember to skip the transition metals. Sodium's in the first column, and chlorine, if you count across, is in the 7th column. After they get in contact with each other, the bully of the group, anion chlorine, steals the electron of sodium. And so when this negatively charged electron travels across the gap, now chlorine has an uneven amount of electrons and it has an extra electron, is therefore negatively charged. Sodium, on the other hand, it's lost an electron. It has more protons now than it has electrons. It's now positively charged, the cation. So what's this got to do with anything? Well, when you dissolve a chemical like NaCl inside of a liquid, supposing that this is the one with it inside, those are going to split apart, but they're going to keep their charges. So we'd have separated atoms of sodium and chlorine floating all around inside of there, and they'd still have positive and negative charges. And let's talk about water briefly now. Water, when you subtract the electronegativities, it's got a electronegativity difference of between 1.2 and 1.8. And so what that means is it's a polar covalent bond. What happens is that even though it's forming an ionic bond, the electrons spend the lion's share of their time around oxygen. The hydrogens miss out. That means that this side of the molecule is negatively charged, and this side of the molecule is positively charged. It's polar covalent. One end is positive, the other end is negative. And what that means is that when you have billions and billions of atoms together of water, they all are clinging together. They're all sticking together with little intermolecular forces. And the only way to get one to separate and evaporate is to give it a bunch of energy via heat. Okay, so water likes to stick together because it's got all of these different charges. Now what happens when we throw in a bunch of disassociated, broken up sodium atoms with positive charges and chlorine atoms with negative charges? Well, it complicates everything. So let's imagine this is our substance. We've got the waters floating around with their positives and negatives. We've got a bunch of sodiums and chlorines with their positive and negatives. What happens? It seems like there's a whole lot more charges involved in there. So if we make the charges more prevalent and stronger, is that going to make it easier to knock one out? Is it going to be easier to make it evaporate? Or is it going to be harder? I don't know. So that's where the experiment comes in. In class, you're going to take two samples of liquid, the salt water and the regular water. It doesn't matter really the concentration. Probably put a teaspoon of salt in the salt water, and it should be enough. And before you start any experiment, you need to write your introduction. That way you can make some guesses as to what's going on. So in your introduction, here's some suggestions for questions that you can answer. First of all, do you think that salt water boils hotter than water or not? And you need to explain your answer. Like, for example, if you say it's going to boil hotter, you might want to talk about the electromagnetic forces that are going on. Remember, there's more charges in there. Okay? The next thing, which is going to take longer to boil, the salt water or the regular water? That's probably going to be a similar answer to your first question. And then finally, it would be a good idea to figure out what lurking variables are going to affect your experiment. Remember, we're going to be taking the temperature here all of the time. So if we stick a thermometer in there, is that going to affect things? What about your beakers? Are they going to be warm before you start doing your experiment? Think about those things, and even more, be creative, come up with ways that you can improve your experiment before you even start it. Now, the experiment should be pretty straightforward. You're going to be measuring the time it takes to boil, and you're going to also be measuring the temperature. And I have a suggestion how to do it. I would measure the temperature every 30 seconds. So, for example, you're going to be making a table like this for both your salt water and your regular water, and every 30 seconds you're going to refresh and take the temperature of your liquid. as it goes from liquid eventually to boiling and gaseous. Now, it doesn't matter if you measure in Celsius or Fahrenheit. Just remember that boiling point of water is 100 degrees Celsius, and the boiling point of water in Fahrenheit is 212. But what about salt water? That we're going to figure that out. Anyway, when it starts bubbling and stops changing temperature, when it gets that hot, then you know when to stop. So hopefully we know that works out. Okay, so what are you going to be doing with this data? You're going to be making a graph, and I'm not going to tell you which goes where, time or temperature. You have two variables, right? But the one that depends on the other, of course, goes on the y-axis. That's the dependent variable. The independent variable, the one that doesn't depend on the other one, goes on the x-axis. And so it would be really helpful to put both graphs on the same chart, or both lines on the same graph. And so what I've done is I've shown a red line and a blue line with the points connected, and you can see that they're both there. And I've included a little key over here. The blue is supposed to represent salt water, and the red one is supposed to represent regular water. Now, I hope your graph doesn't look like this, because obviously our temperature is going up and down and going crazy, so it doesn't look like that. But it will look like something, and you should be able to make some good conclusions out of it, which is where you answer these questions. First of all, what did you find, and which one boils hotter? Okay, that's the most important question you need to answer. And you might want to throw in a little bit of an explanation why that happened. Does it agree with your hypothesis? How does your findings, and how does this compare to your hypothesis? Remember, we wrote the introduction before we carried out the experiment. Were we right? Were we wrong? What did we learn? Don't forget to cite your graph, your data. We are making the graph for a reason, and we need to be able to read it. So if one of the lines is higher than the other line, what does that mean? If one of the lines is steeper than the other line, what does that mean? So those are the sorts of things that you need to talk about in your conclusion. And finally, one of the most important things you need to do is, how could you have improved your experiment? You answer that question. Things go wrong. Sometimes you forget to take the temperature. Maybe you could have taken the temperature more often. Maybe you could have taken it less often. There's a lot of things that you can do to make your experiment even better after you've done it and after you know a little bit more about it. So come up with some of that stuff, throw it into your conclusion, and that should be a good lab report. And then finally, without tasting, you should be able to tell me how to determine which one's salt water and which one's regular water. I think this one's the regular water. Nope.